Good morning, students. Today we
or
are reflecting on things,
or good afternoon, depending on when you are watching this, which if you're doing in the afternoon, you probably didn't do it during the proper class time, but we forgive you.
or even good evening.
Not good night though. You should be in bed.
That's true.
Ooh.
So, Mr. Butterworth, is this like the stuff we were looking at uh, last time when we had translations with this type of notation?
Yes.
And so, if this is just like coordinates, could I rewrite this as like that's the x, so 3 right, then -4 for y would be 4 down?
Yeah, buddy.
And I was very careful not to use the word over because we know that
Yes,
can
I
cause some issues.
appreciate that. So 3 to the right, 4, 1, 2, 3, 4. I say that E winds up right there.
I like it.
D, 1, 2, 3, 1, 2, 3, 4 winds up over here. And F,
Cool.
1, 2, 3, 1, 2, 3, 4 is right there. F prime. How'd I do? Did I count correctly?
That looks good to me because if we then connect the dots, to me, this shape looks congruent to the other one, minus my bad drawing. And we know that translations make things that are congruent because I could slide that back right on top of it and it should match up. All
I
right.
agree. I don't know what that big R means though.
Well, we had a clue because we had the title of this was Reflections.
Ooh, reflections.
Um, and like
I
if
like
this,
look in the mirror and I see myself.
there are a bunch of songs about reflections too. There's
If you
like
say
the
so.
well, there's like the Mulan one. Uh, that's I think Christina Aguilera
I believe you.
sings that one. All right. So if we're reflecting it, would that mean that we'd see a mirror image of it since we're talking about reflecting in mirrors?
I'm gonna guess so. And it says the x-axis, so I'm gonna guess we go over the x-axis. So like F would wind up that I almost did the y-axis. That was a close one. Up here. So that's where F double prime, because this is the x-axis right there.
Oh, and since this is D prime, E prime, F prime, that's the points that are already primed, and you're making that have two primes because that's like the transformation of a transformation.
Yes, it's a double prime.
Cool. All right, so that's F double prime. And then for like D prime, this is the x-axis, so it's going to reflect. If that's 1, it's going to be 1 down for D double prime.
I agree. And I did E double prime just for fun. Although my E looks very bizarre, but
How
we're going to roll.
bizarre. And then if I connect these points, I can see that I could like fold that over the x-axis and my single prime and double prime would overlap.
I agree.
Uh,
We did great.
I might even say that's symmetric. Boogie,
I think
woogie,
that
woogie.
I think that's fair.
All right, so we've got, uh, is this showing corresponding pieces? Is that what the attempt is here?
I think it's showing like you'd read it BUG clockwise, and then when you reflect, you read it the other direction because the things that are closest to the line of reflection are still closest to the line of reflection, but the order might have flipped.
Um,
Whereas in a translation, like the orientation is always the same. In a reflection, it might not be.
would this be easier to think about like you want to refer to them in the same order of like the pieces that like the smallest angle I want to say in the same place as the smallest angle here?
Yeah, those are called corresponding parts, and you want to make sure you match.
Um, because I feel like if I think about this, oh, I have to read all triangles clockwise unless they're reflected. That's what this says to me, and that's really confusing.
I agree that that would be a wacky rule, and that is not the intent. I don't think.
Cool. So
I
this
think
is
it's just
just,
pointing out that the order changes.
but they are still congruent because you could flip them
Yeah,
and end up putting them on top of each other.
right.
And this is kind of a definition of what a reflection is. That
Yeah. So that last sentence, the orientation of the figure reverses. I think that's part of the intent of that previous picture.
oh, okay. And what we had talked about, each point maps to another point the same distance. That's showing how far it is from that line of reflection.
And do we need to explain what maps means? Because I don't know that we've used that terminology before.
When I think about mapping, it's just kind of connecting. So if this is point A and we did something to get point A prime, we use the word mapping to say that point A is transformed into A prime. We also use this, if you remember back in kindergarten, you had things that looked like potatoes.
Oh,
And you could talk about how the input goes to the output. And this is a mapping as well.
did you actually do that in kindergarten? Because I don't remember doing that in kindergarten.
No, but I had my favorite professor in college on the first day of class drew this on the board and said, "This is a potato. You did this in kindergarten." And then kind of went on from there. So I always talk about that.
Love it.
All right, so we're reflecting stuff across a line. There's a lot of dense stuff in here that just kind of makes sense based on how we think about making reflections. There's some discussion that the line of reflection is the perpendicular bisector of the segment that connects the two mapped points. That's super dense. All that's saying is that B is the same distance from this line as B prime. Also, we measure distance with perpendicular segments.
Which I always remember because when you go to the doctor, they don't take the meter stick and put it like, 4 feet away from you and do this weird diagonal thing to you. It's right up and down. So that's how they measure your height or your distance.
Yeah. So there's a lot of stuff that's not actually important to our understanding of this here.
It's just adding some mathematical words behind what's going on.
Mhm.
And if you need them and you like them, by all means use them. If you don't need them, then don't.
Don't worry about it. All right, so we're going to reflect a point across a line. And I noticed that we're using the line y equals 1. All right, so I'm going to go 1. And I'm just going to draw the positive x side of this.
Wait, how did you know it was that kind of line?
I know that I've got to find the y coordinate of 1, and I've got to make a line that goes perpendicular to that axis. So if that were x equals 1, I'd go where x equals 1, it's got to go up and down through that.
Wait, you said the word perpendicular. Why do I have to be perpendicular?
I would actually use the word orthogonal, but I'm not going to use that word in this context. It's got to be perpendicular because I know that x equals and y equals lines are all of the coordinates that have that as a value.
So would another way to think about it be plot some points whose y value is 1 and connect them?
Sure, that would work as well.
Okay.
Yep.
So I'm supposed to reflect across that. So would it be helpful to note how far that is?
I think so. And if we're going from, I was about to say from 3 to 1, because I'm not fully awake yet, but if we know this is a y coordinate, so if I'm going from 4 down to 1, is that supposed to be a brace?
I can't do those. Yeah, see, I can't do that.
That's going to be 3.
One of many deficiencies. So I have to. Yeah, I'll try harder. So I got to go 3 down.
That one's not bad. And here I tell all my students that a brace is one of the mathematical symbols that we're bad at drawing, but we get better with practice. Apparently, that's unless you're Mr. Butterworth.
I can't do it. Like my calculus students make fun of me because we have an integral symbol, and they're like, "It's just 2 integral symbols." I can't even do it put together, and I'm just like, it doesn't make sense in my brain. I can't do it. Anyway, so I'm going 3 down from 1. So if I go 3 down from 1, then I get to -2.
I like it. And we're keeping the x the same because we're just flipping it over a y equals line.
I pick C.
I concur. All right, so we can use the reflection of a line. You can use the equation of a line of reflection. I was trying to figure out why I was saying reflection twice in function notation.
This is that we're using our book's notation, even though we're not using our book very much, just in case you see it. It's more likely that we will tell you this information, that we will reflect across the line y equals x, although generally we will not necessarily do that to you because that's kind of mean.
It's true.
But that's what this notation means.
Although this one's not too bad because it has a fun rule that works pretty easily, but most other lines are kind of gross to reflect around.
It's true. The next page is going to make you hurt.
All right, so this is
basically all this is saying is if you reflect something, its image is the same size, it's congruent. So you preserve distance, that means the lengths are the same. You preserve angle measure, that means the angles are the same. So that's the congruent thing. If you have a pre-image, its image is congruent after reflection or reflections.
So we kind of started from the idea that things were congruent with certain transformations and have been talking about different transformations that produce congruence. It's like this is kind of starting from this is what a reflection is. Oh, by the way, this is congruent as well.
Yes.
So again, like this is a lot of mathy words. All we need to know is that these things are congruent. All right.
The points, graph and label. Okay.
Mr. Butterworth, is this a good one for them?
I think so. I think one of the ed puzzle questions could be, where does like point A wind up?
I think so too.
So that's A, negative 3, 4. And that notation, once again, means reflect over the y-axis. That's B, 0, 1. And then C, 4, 2. C is 4, 2. And so, does that yellow dotted thing the y-axis? Is that what you just did?
It is, which I'm going to call x equals 0.
There's an interesting thing going on here. We have a point on the on the y-axis. So what happens if we're trying to reflect across that?
I feel like that would end up being like, if I think about this as a mirror, if I put my finger on the mirror, the reflection looks like it's also on the mirror.
So you're saying it doesn't go anywhere?
I think so.
Okay. So then since we're going across the y-axis, A has got to go from the left to the right. So that's going to be at 3, 4. My drawing was not to scale at all. I apologize. 3, 4. And then B has to go from the right to the left because it's flipping over the y-axis.
C.
So negative 4. Sorry, C. Negative 4, 2. Again, not to scale. And an interesting thing to note is what is the same between these points and what is different?
I noticed that all of the y values are the same. None of those changed.
What about the x values?
I noticed that 2 of the x values became negative or positive, depending on, like, they flipped signs. And then one of them stayed the same.
Is that because it was 0? And if you flip the sign of 0, it's still 0?
That makes sense. So since 0 doesn't change sign if you multiply it by a negative, it stays non-negative and non-positive. Then we're saying that the x's are going to change signs if we reflect across the y-axis, which makes sense. Because we're going from like quadrants 1 and 4 over here to quadrants 2 and 3 over here, and that's positive x and negative x.
Oh, now you're throwing quadrants in there? What if I know, huh? That's a story for a different day.
I have been informed that they talk about those in middle school, so we're okay.
Yeah, but middle school is like the worst part of our lives, so they might have forgotten.
All right.
Each triangle in the diagram is a reflection of another triangle across one of the given lines. How can you describe triangle 2 by using a reflection rule?
All right, so this is where we have to kind of describe what's happening based on what we see here. I noticed that it looks like 1 and 3 go together because those are like sitting across this horizontal line. I keep on saying it's the x-axis, but it's the M
Mhm.
line. So I'm going to say that 2 and 4 have to go together as well.
Mhm.
And across, I didn't kind of purposely do, but across this line K.
So if you're asking us to describe triangle 2 using a reflection rule, are they trying to say that if we reflect 4 across K, we get 2?
That makes sense to me.
So we could write that in words. The notation our book would use would be reflect triangle 4 across the line K. Do I just put K? Because it's not like a.
I think that's fair. That makes me
Um,
kind of uncomfortable.
it does, but feel free to put that in words. So reflect triangle 4 across line K. I'm going to write that down in case you forgot what I was saying. Reflect triangle 4 across K. Because if you're like my children, when I talk, all they hear is wah, 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 wah.
I don't think they'll get that reference, Mr. Butterworth.
I am hopeful that 2 of them will, and one of those people will email us. See, that worked last time. Someone emailed us. Wait, I had something on that.
Oh,
Don't go. Please don't go. So, if I look at this picture, I see another transformation going on. If I look at triangles 2 and 3, the orientation of those triangles is the same. So it looks like we took one triangle and just slid it to the other triangle. That would be a translation, which we have already talked about.
it's true.
We can go now.
You didn't want to talk about the rotation that was there either?
No, because we don't know those yet. I didn't want to scare them. If we rotate G across T, we get G. If we rotate H across T, we get J.
Reflect. You said rotate
I
twice.
blame you because you said the word rotate. If we reflect D across T, we get D. So I notice that both G and D don't go anywhere.
Um, I'm going to say that there's a way that I want to do this, which has more math than we've currently talked about. And there's another way that I think if we consider this a triangle on the left half and on the right half,
Mm.
that will use math that we know. Because if this triangle GHD is reflected across line T, which appears to be the case because we're given the reflections of each point to make GJD, we know that reflections are a congruence transformation, that they preserve distance. So the segment GH would have to be the same length as the segment GJ.
That was super fancy words. So is it fair to say if I take the triangle GHD and reflect it across T, I get the triangle GJD, and those triangles are the same, and therefore the slanty parts are the same?
I agree.
Okay. Now, I think we're making an assumption that we know what isosceles triangles are. So an isosceles triangle, I think we know it, but I'm going to reiterate it. An isosceles triangle is one in which at least 2 sides are the same.
Ooh, use the British definition. I like it.
I did.
I was going to ask and cause some trouble, but you already went there.
Yeah. I mean, technically speaking, it depends on how you define things, but
Yeah.
at least 2 sides are the same.
And here we have 2 sides that we know are the same because they're reflected. So therefore, this would be described as an isosceles triangle.
That was a fun one. What do we got here? Ooh, okay. So these are good ones for them to do, just like we did with the translation section.
I agree.
Reflect across y equals -2. I think maybe it would be helpful for us to draw those in so that they at least have that help. So y equals -2. Mr. Carlson talked about perpendicular or orthogonal. I can't talk. You can also just plot points where y is -2, and you'll get the dotted line that Mr. Carlson is so kindly drawing in. So you need to reflect that quadrilateral across the line y equals 2 that Mr. Carlson drew in. We should also help them and tell them what that letter is. I
That
think,
looks like an hourglass. I'm gonna.
okay, it's an hourglass. I really can't tell. It might be an X, but the letters also aren't in alphabetical order because who knows? So who knows what it could be?
It's an X now.
Okay. And then you drew then the x-axis. Is there an equation for the x-axis? We have y equals -2 for that line in number 1. Is there an equation for the x-axis?
Well, what are the y coordinates on the x-axis? Like, what are the heights here?
Well, like that's 0, 0, and 1, 0, and 2, 0, 0. Oh, got it. Okay, so if I see y equals 0, that's also known as the x-axis.
I like it.
Cool. So I just need to do those reflections. And then this is the same idea. All you have to figure out is what the line of reflection is.
Maybe it was a K.
It could have been like 4 different letters. Who knows? Anyway, drew me off. You just have to figure out what the line of reflection is. And
Oh,
I
so
think I think I want to do number 8.
yeah, I think that's fair. Is it a reasonable thing to say that I can see where this reflection is happening because I can see where I could like fold this in half? Or that I have 2 points that are the same for their image and the pre-image. So we know that line of reflection has to go through there.
I think both statements are fair. You also said I can see, so I started singing, well, mouthing the words quietly to I can see clearly now.
I
But
like it.
we won't go there. So that's like a line there. It goes through 0, 0. The slopey slope looks like it's -1.
Cool. I agree.
So if I think of that y equals mx plus b thing, because I know that's in the humans' brains, m is the slope, and we just said that's -1, and b is the y-intercept, and that's where the line hits the y-axis, and the line here hits the y-axis at 0, 0. So b is just 0. So the purpley color would be a reflection across y equals -x of the black one.
Would it be okay for us to write that like the -1x plus 0 if that makes us more comfortable?
Totally fine.
Cool.
We did it, Mr. Carlson. We're the best.
It's true.